Yeah, welcome. My name is KB of Fabrausch, and yeah, I'm here to talk about practical Softsynth design. So, a disclaimer first: if you already have written a complete software synthesizer, this seminar is maybe not exactly for you because you might get one or two tips, but of course, 45 minutes are not enough to go in depth. So I will explain a few of the design principles and a few basic DSP principles in a quite superficial way, but you can of course ask questions afterwards if you want to get into the gritty details. Yeah, good. So yeah, let's jump right into the very basics. How do I get sound in and out of my computer? I mean, this seems trivial, but I've run across enough people who don't even exactly know what those WAV files are, what they're dealing with. So what we're dealing with are samples or PCM waveforms. The thing is following. You have sonic waves. These sonic waves get, for example, into a microphone where they're converted into voltages. Those voltages are then sampled or measured at certain intervals and translated into numbers. They are then stored in the computer, and sorry, and as soon as you want to play them, the computer will get those numbers and convert them back to voltages, where they go through your amplifier, through your big Dolby digital home theater, whatever system, and then go into the loudspeakers where the voltages are converted back into sonic waves. So the samples, the data, which are in wave files, are practically a measurement of the air pressure at this very moment in your ear. So PCM stands for pulse code modulation, which is a quite archaic method of digital to analog conversion, which isn't used anywhere anymore. But shortly after I typed this, I found out that the Super Audio CD works this way because it doesn't really use voltages. It just uses zeros and ones in really rapid order to produce those voltages. So this is why it's called pulse code modulation, because it does pulses and tries to get a constant voltage with it. Anyway, those intervals at which the waveform is sampled is called the sample rate. It's probably, you know those numbers, 44,100 or 48,000 times per second. And so you must, so the signal is sampled in those constant intervals, and numbers are made of it. And those numbers are discrete, which means, of course, a voltage can be anything. A voltage can be square root of 2 or p volts or whatever. But the values you get are discrete numbers, quite normal, rational, or even whole numbers. Okay. So how are these waveforms stored in the PC? The waveforms are stored as stream, as a giant memory block with sample after sample after sample after sample. And because it's inefficient to send stuff to the sound card, sample for sample for sample for sample, just imagine a driver which holds the PC every 44,100 of a second. We use whole buffers with about 1,000 or 2,000 or 4,000 or whatever samples in them, and process them at once. So it's also feasible for our own code, for our synthesizer code, to process whole buffers instead of single samples, because if you have a big chain of modules which are processing the sound, it's like a few kilobytes of code that have to be run through for every sample. And if you know coding a bit, you know what the CPU cache thinks of things like that. So it's easier to take small buffers which completely fit into the CPU cache and then apply short sequences of code, so single modules, on the whole buffers. So it's quite faster. Yeah, and the thing is that every sound API has a method of sending whole buffers. There are no sound APIs which work like OpenGL, like GL sample or something like that. It's like you always send whole buffers of whatever amount of samples to your operating system, whatever it is. If we're dealing with stereo or multi-channel waves, the samples are either interleaved. That means if you have the data, we have one sample for the left channel, one for the right, then we have one for the left, one for the right, again one for the left. Or this is how VST or ASIO, those Cubase standards work. You just have two buffers, one buffer for every channel. Multi-channel waves like 5.1, if you want to submit something in the Simulatio 3D compo perhaps, work either with 6 interleaved samples or 6 buffers. So, well, let's get into the gritty mathematics now. If we sample things, we take measurements. So, a guy called Fourier has found out back then, a few hundred years ago, that every sound consists of many tones at different frequencies. If you have a wave, this wave is made up of single frequencies, which are represented by sine tones. A sine tone sounds about this. And you can build every sound of those tones. For example, if I play 2 sines on an octave. Wait. Hahaha. Du kannst mich auch ein bisschen lauter stellen übrigens noch. Okay, if we play two sounds at 1 octave interval, it sounds this way. So you can't distinguish the 2 sounds. It's like one sound with a different sound. Or I could use 3 of them. So every sound is made up of single sine waves. Even noise is made up of single sine waves, perhaps an infinite amount of them at the weirdest frequencies. So now the second thing is, oops, if we want, sorry, the problems of being long-haired. Just a moment. One, two, yeah, better. Okay, so to find out that the signal is changing, if we sample it, we of course need more than one sample, at least 2. And the conclusion of this, if we think about it, is the so-called sampling theorem. If we sample a thing, a wave at about 44 kilohertz, the highest frequency we can possibly sample is 22 kilohertz. Because if you imagine the wave, sorry that I hadn't time to present a good picture of that. If you imagine the wave, which a sine wave, which goes this, the best chance that we have is that we sample at the peaks and at the valleys and at the peaks and at the valleys. So per cycle of a sine wave, we need 2 samples. So if the sine wave is shorter than 2 samples would suffice, we have so-called aliasing. Aliasing occurs as soon as the frequency is more than half of the sampling frequency. And the nasty thing about aliasing is that it introduces new frequencies below this so-called Nyquist half frequency, which are completely disturbing. I would like to present something, but no, I can't, sorry. So the problem is, if we record sound with a sound card, a sound card has analog filters, which filter the signal at half of the sampling frequency. So we don't have any problem at all. There are no waves in the input signal of a sound card which could be disturbing. But if we synthesize waves ourselves, we work with mathematical models. And mathematical models essentially have an unlimited number of higher and higher and higher and higher frequencies if we don't synthesize a sine. And we have to take special precautions, that is, for example, filter them or use a method of synthesis which cuts off those too high frequencies before they occur. There are many algorithms for that. There are much too many algorithms for that to go into detail here, but you can, of course, ask me afterwards how it's worked. Okay, the whole principle of the synthesizer I've wrote, the V2, is subtractive synthesis. Subtractive synthesis means you start with a certain bass sound and then only take away from this bass sound. You have a bass sound which has a lot of frequencies, and then you use filtering or effects to take away frequencies you don't want. So this is the theory. In practice, it looks different. We have filters which are resonant, which can amplify frequencies. We have effects like flanger or delay features, which even can introduce new frequencies to a signal. So subtractive is maybe not really the right term, but still people are calling it that way. So the principle is following. You take a few oscillators, and then You run them through effect, effect, filter, filter, effect. You split them, run them to another effect, and this to a filter. You mix them again, so you have your base signal, and you try to screw it up as good as you can. And the first step to good sound design is to enable the musician to screw it up as good as he can. And the biggest and the most important thing, to modulate those screw-ups while the sound is running. So we come to the first basic building blocks, which are those oscillators which generate sound. For example, we have the sawtooth wave. I hope so. The sawtooth wave, you should maybe know it. It's sounding like this, and it's looking like this. It's a sharp sounding and the basic building block of most synthesizer sounds, because it has a good even distribution of its frequencies. And to go into one algorithm, if you look at this wave and we try to find out how to synthesize this, the trivial way is just take an integer variable and then for each sample add a constant to it. So we add a constant, we add a constant, we add a constant, we add a constant, and then the integer variable overflows and starts again here. So essentially, synthesizing a sawtooth is one addition per sample, if we want it that way. The problem is, this would be a perfect mathematical model, and this would introduce aliasing like hell, because all the higher frequencies are in it. So we have to take precautions to eliminate those frequencies beforehand. But it's a good start. It's for example, for 4 kilobyte synthesizers, it's the best way. It's like one float add for synthesizing a whole sawtooth. Yeah, the sign I already showed it. It's sounding like this. It's the purest tone, and you can make every sound of combinations of sine waves. For example, there are synthesizers which are called additive synthesizers, which take, let's say, 100 sine waves at different frequencies, at different volumes, and make their sounds that way. Which they are a beast to control, but they offer unmatched flexibility, because you can synthesize every frequency you want without being restrained by what a filter does or something like that. Then we have the triangle. The triangle is quite easy too. It's like, it not only looks like a digital version of a sine wave, it also sounds like a digital version of a sine wave somehow. Like a sine, but with a few additional frequencies in it, which is a bit higher. Then, one of the tricks my synthesizer had that I haven't seen so far in any other software synthesizers in the demo scene is that you can morph triangle into sawtooth and back. Just by taking oopsie. Gizmo? Yeah, can anyone put this
Driving. Come on.
Okay. Yeah, faster please. Okay, but by changing the slope, you can morph a triangle into a sawtooth and back. And this sounds, for example, like this. Which start with a triangle, and now we slowly morph it into sawtooth. So we have a whole spectrum of sounds just by essentially one formula, which either can do triangle or sawtooth or anything in between. Then we have the pulse wave. The pulse wave, you should know that every time a computer boots up, it sounds like this. This is a pulse wave. A pulse wave is used for a PC speaker because you essentially have one bit that goes on and off and on and off and on and off. And you can modulate this pulse wave just by changing the ratio between on and off. So this is 50% on, 50% off. If I say 75% on and 25% off, it sounds like this, and it goes sharper and sharper until it disappears. And if we modulate that while the sound is running, we have a sound which might sound like typical C64 sounds now. Where's my mouse? Oh, there. Oh, wait. This keyboard doesn't work. Could use Could last a bit, sorry. Okay, and last we have noise. Just wait. I borrowed this today, I don't know how it works. Why is it showing error? Oh, because it doesn't have power, perhaps. Sorry. Okay, the noise waveform. The noise waveform doesn't have any power outlets in R here. Which doesn't work. Okay, let's reboot Logic and it should work. The noise waveform is random. You see that not? Because something went wrong. Whatever. Ah, okay. The noise waveform is random. Random is the usual random function. If you want to implement it, it's perhaps one multiplication and one addition. There are enough papers about that. And the thing about random is that really all frequencies are in it. From 0 Hertz to your Nyquist frequency, they are all in it, they are all evenly distributed. So this is perhaps the waveform, for example, for sound effects. And if you really want to shape a sound and do weird things with it, noise is the perfect base because, better. Noise is the perfect base just because everything is in it. And we're dealing with subtractive synthesis by using a base and then subtracting from it. Okay. Mixing several sounds. So at the moment we only have one sound. Mixing two sounds is easy. Just add them together. Just use one buffer with one waveform, another buffer with another waveform, add those buffers sample by sample, and write them into another buffer, and so we have two sounds. But there's a common misconception I have run across, which mod players do since like the dawn of software rendering. Most people think, oh, but two sounds are louder than one, so it could overflow and clip, so I have to decrease the volume somehow. No, this is complete bullshit. I mean, for example, take a violin and a cello player. The violin player starts to play, and 10 seconds later, the cello player kicks in. Who of you has really heard that the violin gets more silent then? Who of you knows a violin player who plays at a low volume instead of a high volume because he knows that a cello is next to him? Exactly nobody. So the volume should be completely in the hand of the musician. You shouldn't decrease the volume just because you have more channels, because the musician can do that. The musician has an ear for it. The musician does the sounds and knows how loud these sounds are and what comes out at the end. So if you mix, just add them. Okay, changing the volume, of course we want to do that, but we want to do that manually, not automatically, is easy too. Just multiply a buffer with a constant. That's all. I mean, double the values and you get double the volume. This means you should place volume controls wherever you mix, because somebody has to decrease the volume when mixing, because it would be completely overloaded otherwise. So just place volume controls wherever mixing can occur. For example, if you have multiple oscillators, which go down to one sound, or if you have multiple voices, which build, for example, a chord, or if you have multiple channels which build a complete song, at these points it's feasible to use a volume control to let the musician mix and match the volumes. Yeah, combining waveforms is one of the other keys. Most synthesizers I know only take one or two oscillators without providing flexibility, and the thing is, the good sounds come as soon as you try to combine them. For example, I take one sawtooth, it sounds this way. If I take two sawtooths and detune them a bit against each other, so make the one play a bit lower and the other play a bit higher, it sounds like this. much better. If I take a third sawtooth and transpose it, for example, an octave up, then, if my mouse would work, then the sound is even more interesting. So mixing oscillators is really, 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 really important. Don't stop when you've got one sawtooth, because it will sound like one voice of the C64 and not like a complete software synthesizer. Nothing against the C64, but I think you know what I mean. So then oscillators, if we got multiple oscillators anyway, we can modulate them with each other. There are a few methods of modulating. For example, amplitude modulation. Amplitude modulation or ring modulation means that we simply multiply two waves with each other, which gives strange effects because if you know maths, you know the addition theorems. So if we multiply two sine waves with each other, and every sound is made up of sine waves, we get two different sine waves with the frequencies added and the frequencies subtracted from each other. So ring modulation is perhaps not really suitable for music, but for sound effects is great. For example, if we start with one sine wave and then ring modulate another sine wave to it. Just wait. And then detune the other. We get things like this. And if we try to use this with complex frequencies, like one triangle and one sawtooth, we get really strange looking things. You might recognize the dirt in the sound. That it really starts getting dirty when it's higher. This is the aliasing. Because my ring modulation introduces new frequencies, and even if your basic sounds have filtered all too high frequencies, introducing new ones can introduce too high ones. So essentially, if you try to fight aliasing, you have to fight it at every fucking step. And even I did not. So the good thing is, if you write a synthesizer yourself, you as a musician know what keys not to press. This is part of the secret. Another kind of modulation is frequency modulation. This is what the old Yamaha synthesizers like the DX7 or the Adlib sound card uses. We take one sine wave, sine wave, and now we take another sine wave, which can modulate the first sine wave. Just wait. God, I should have decelerated my mouse a bit. And if you watch closely, it really sounds like an Adlib sound card. So this is frequency modulation. Frequency modulation. Most people trying out frequency modulation really try to modulate the frequency, which doesn't work, because if we have frequency modulation and we say, okay, when the modulator wave is up, so the frequency should be 10 hertz higher. Those 10 hertz are always 10 hertz, and the scale of frequencies is logarithmic. So one octave more is doubling the frequency. So 10 hertz are a different kind of measure regarding on which note you play. So if you try to modulate the frequency, it will sound different with each different note, and this is not exactly what we want. This is why all FM synthesizers I know don't use FM, but phase modulation. The phase is, if we take a sine wave, the phase is the position within the sine wave, which we have at the current sample. And we can modulate this. We can use the carrier to push the phase forward and backward. And the thing is, now it's irrelevant how high or how low the note is. Pushing the phase forward or backward always gives the same results. And I mean, if you base, for example, your oscillators on a counter, which looks up a sine wave, then it's completely easy because you just have to add the modulating wave to the counter and get the resulting FM modulated wave. That's all. Then there's one thing, one modulation which I haven't done so far because I haven't yet thought of a good method to get rid of aliasing there. It's oscillator syncing. So if we have an oscillator which does a sawtooth wave, and we have another which does a sawtooth wave at a different frequency, we can let the other oscillator restart the first as soon as it crosses their own restart border. This gives strange effects. This gives really high, sharp sounds. I don't have an example here, sorry. And the problem with that is it's, of course, totally trivial to implement, but if you go the trivial way, the aliasing will kill you, and it will sound like total shit. Trust me, I tried. Okay, filters, next thing. Filters are perhaps the most important things, and filters are a topic about which several 1,000-page books have been written. So don't expect from me that I now explain to you how filters work. Because there are several 1,000-page books, there are like millions of papers with different filter designs on the internet, and understanding them fully requires a good grasp of mathematics. So I won't really explain how they work, I just explain now what they do. Filters filter away certain frequencies. They attenuate low frequencies or high frequencies or everything around a certain frequency, and they can also emphasize certain frequencies. So if we get back to a sawtooth, and now we try the first type of filter, the low-pass filter. The low-pass filter sounds about like this. It filters away high frequencies and lets the low frequencies pass. This is because this is why it's called low-pass. So we can already play bass lines with it. Then there's the high pass, which does exactly the opposite thing. It filters away low frequencies and lets the high frequencies pass. And it sounds like this. The third type is the band pass, which only lets one, not exactly one frequency, but a bunch of frequencies about shape this if you look at it in a spectral way. Wrong button. Wait. So it lets through only certain frequencies. And we have the notch filter, which filters away certain frequencies and lets everything else pass. Which is great for modulating stuff. And we have the all-pass filter, which lets everything pass. This may sound funny because why do a filter if it lets everything through? But first, it modifies the phase of the signal a bit. And then we have the next topic, resonance. So filters not only can filter away things, filters also can emphasize things. So if we take a low pass again, and now emphasize the frequency at which the low pass filtering occurs, emphasize it a bit more, it looks like this. It sounds like this. For example, we can do this with every filter type. This is a high pass filter. This is a band pass filter. This is the all pass filter, which now only emphasizes a certain frequency and lets the rest go through. So, different filter designs differ greatly in the sound. So if we have an IAR filter or state variable filter or whatever, it totally depends on your implementation how the filter exactly sounds. Some filters are cutting off the rest if you turn the resonance up. My filters, for example, only emphasize without cutting, and they all sound really, really different. And it's feasible to try out several filter models just to find out which sound suits you best. Okay, and the thing is, what you now want is multiple filters per sound, because one filter sounds quite boring, and so you want many filters. Many filters means that we have, for example, two filters, one high pass and one low pass after that, which also cuts the high frequency in a serial manner. And so, for example, we can isolate certain frequency ranges, which a single bandpass filter isn't really capable of. So we can specify a low and a high border of the sound. Or alternatively, we route the filters in parallel, and now let pass only the lowest and only the highest frequencies, which sounds about like this. Just wait. This is, for example, the typical panic or hip-hop bass. It's still done with one sawtooth. So this is why you not only want many oscillators, this is why you want many filters. So to have, almost unlimited possibilities. So now the most important things, modulation. I mean, honestly, this sounds boring. Because it doesn't do anything. So what we do want now is modify the sounds while they are running. For example, with LFOs. LFOs stands for low frequency oscillators, and they are oscillators which, oscillate at a really low frequency. So we can, for example, route a low frequency oscillator to the pitch of the sound, to the frequency of our whole note, which about sounds like this. So we can do a vibrato with it. Or we can try to modify not the pitch, but the volume, which then wait. Where is it? Sorry. Here it is. And it doesn't work. Just this. Why doesn't it work? Because I'm too dumb, perhaps. Okay, wait. So if we modify the volume, we get a tremolo-like effect. Or which is maybe the most interesting, we can modify the filter with this LFO. So if we modify the cutoff of the first filter, and then turn up the resonance of this filter a bit, we get a sound which may sound funny and ugly, but it's at least interesting, more interesting than the thing before. So the other source of modulations are envelope generators. Envelope generators, put an envelope around the sound, which means that the sound, for example, rises as soon as we press the key. Then this is called the attack phase. Then decays a bit. This is called the decay phase. Then keeps the same level as long as we press the key, which is called the S sustain phase. And then gradually fades out if we release the key, which is called the release phase. So we have this sound, and now we can apply an envelope generator to the volume. We do a slow attack, then decay up to, let's say, half the volume. Why? This is. Then a decay to, let's say, half the volume. And if we release it, we can let it fade out. At least I think so. This is the problem, okay. Writing envelope generators is easy because it's just a thing that counts up a variable, counts down a variable, and reacts to events and counts up and counts down. And the trick is then to, as we want to modify the volume, to multiply this envelope, the output of the envelope, with the output of a sound. And so this will happen. What we also can do, Gizmo's said I have 10 minutes left, that's not good. What we also can do is use this envelope to modify the filter. which we can do to do a like sound. I do it now by mouth, but because it's faster, sorry. We can also use the note velocity, which you may recognize. I can modify. Yeah, I can modify the volume of the sound by the amount I press the key. I can also use the number of the note, the pitch of the note, as modulation source. So, for example, I can make the filter higher on higher notes. As you see, and now the filter vibrato effect is higher here than it's here. I can also do the opposite. I can do high filter on low notes and low filter on high notes. So this is modulation. So we also have modulation sources like those MIDI controllers, which are on this wheel or something like that, so that the musician can paint envelopes in his favorite sequencing software and modulate the sound further. So, okay, I think I have to rush a bit, sorry. Then we have effects. Distortion is maybe the most interesting effect because it destroys sound, and destroyed sounds are always great. Distortion does, for example, what happens if you turn up an amplifier too loud. So let's take the sound, and now let's try to distort it. Let's try to distort it by the normal thing, a clip. So the wave goes up until it reaches the upper border of your sampling, and then it's clipped there. So it hits the border and stays there until it goes down again. So if we want to use clip distortion, it sounds really hard and digital. There's another saturation distortion. This is, for example, what tube amplifiers do. They don't really go up and go up and go up and then stop going up, but they go up, go up, go up, and then slowly fade until they reach the upper border, which sounds warmer. For example, the clip is harder. Okay, the sound is maybe a bit unsuitable for that. Then we have the bit crusher. The bit crusher is great because it crushes bits. Like you have a 16-bit sound card and you want to pretend that you only have a 2-bit sound card. And this is exactly what the bit crusher does. So if we take the sound, now we can reduce bits from it. And really, really, really destroyed stuff. And the last thing is the decimator. The decimator just pretends that we have a lower sampling rate. And the great thing about decimators is that this is the one point where we want to have aliasing because we want to let it sound dirty. This is, for example, easily done by just using one sample and taking it 3 times and throwing the others away, then sampling again, using one sample, taking it 3 times and throwing the others away. So it's a quite cheap effect, but which is at the moment in modern electronic music quite heavily used. Then we have chorus and flanger. Chorus and flanger use delays, which change their delay time to broaden the sound or to fake multiple instruments. So if we have a bass sound again, I can, for example, start a chorus, which slowly modulates its own rate. And if we listen to it, it's stereo. Then we can introduce feedback into these delay lines to feed them back again and do things like robotizing effects or even make new frequencies and sounds. This is still the same bass. Or by modifying the delay times, we can have different effects. For example, if we do the delay time slow, we have a so-called flanger, which plays around with the overtones a bit. This effect is quite known, I think. Okay, next effect, compressor. Compressors are important because compressors are really great for mixing and mastering. What they do is reducing the dynamic range of the signal. Reducing means everything that crosses we have a signal that has a certain volume, and as soon as it crosses a certain volume threshold, the compressor starts to decrease the volume to cut it down. And you can control where this threshold is. When it starts to decrease the volume, you can control how fast it decreases the volume, you can control how fast it increases it again, and you can, of course, control how hard it is. And you can use that to make things louder, because you can now turn up the final volume, the volume of the whole channel. And the result is that low volume signals get loud, while high volume signals stay loud. 5 minutes? Okay. The final effect, so you can control the loudness of a voice much, much, much better than you can without a compressor. For example, if you know the Candytron soundtrack, I made heavy use of compressors there to mix and match everything, because if we compare it to FR08, where it didn't have the compressor, for example, the bass drum is horrible on normal PA equipment or normal stereo equipment, because the bass drum doubled the whole signal to so that I can hear it at all. And if I had a compressor, I would cut down this volume curve that the bass drum does to that, and increase it a bit, and then I would have had a bass drum without letting it destroy the whole signal. So in Candytron I used the compressor quite a lot to create a much better mix of everything. Also, you want a compressor in your master output signal, which comes out of the whole synthesizer, because then you can avoid volume peaks, like suddenly you have a big chord with 10 notes at once, and this chord totally stands out and is like 3 times louder than the rest. And with a compressor can then compress it back, and as soon as the compress it down, and as soon as the chord ends, get the volume back to normal. So you don't have either distortions or too silent music, just because there's one note which stands out. So there are also, what I didn't do so far, equalizing and phaser. Equalizing is like a filter. It's like many filters. It emphasizes certain frequencies and can decrease others, but equalizers are there to really control a broad range of frequencies that you want to emphasize or diminish. So you can really shape a sound with equalizers. They are like those graphic equalizers you normally find in stereo equipment, where for each frequency band you have one knob to turn. Or there are so-called parametric equalizers, which you can set to a certain frequency, like about 1 kilohertz, about 500 hertz, around 1 kilohertz, and then about double the volume or something like that. And there is the phaser. If you perhaps know the demo from MFX, the Universe Part 2, the Planet. It has those really spacey chords, which sound like the best of all 80s space music ever. This is done by a phaser. A phaser is several all-pass filters, which are sweeping around with a frequency, and then create really this sweeping, completely spaced out sound, which I didn't do so far, but which I definitely wanted to do. Okay. Last thing, flexibility. Flexibility is important, as you might have heard now. The more parameters you have that you can modify, the more modules you have you can put together, the better. And most demo scene synths I've run across so far, mismanage this flexibility a bit. They have all the modules. They have oscillators, they have filters, they even have delay-based effect or compressors or something like that, but you can't really combine them to form interesting sounds. Anyone of conspiracy here? Good. So, for example, the conspiracy synthesizer has the problem that, they made 3 or 4 demos with it, and it sounds the same sound-wise. I think that's the reason I had one look at them. And they also trapped into another trap, because you could do a synthesizer modular. That is, let the user full control which oscillator, which filter is wired with which, and here and there. But they come at a cost, because they have unmatched flexibility, but this also means unmatched complexity, because as a musician, I really do not want to click 100 modules together just to get a single sound of it. Of course it's fun and it's great and you can do the weirdest stuff with it, but it's not really practical for making music. That's the thing. For example, in the V2, of course you can download this. This is because this is why I don't show it, because every one of you could download it from my page and try it out yourself. I have done a fixed setup of components. I have to finish. 2 minutes? Okay. I've done a fixed setup of components, and so what I have is like 100 knobs I can turn, which are, for example, okay, of course they are not flexible enough, but they are flexible enough to do much more than with a modular synthesizer, where you lose your motivation on the halfway. That's the problem. Most people would stop getting great stuff out of a modular design before it can surpass a fixed design. That's the problem with modular synthesizers. So, of course, it's tempting, but I wouldn't really recommend it for a start. It's good for the second synthesizer, but not for the first. So, conclusions. We need single, simple modules doing simple algorithms, which process a good bunch of samples together and pass complete buffers off to each other. Of course, there are effects which work sample by sample by sample. So those you have to calculate sample by sample by sample. But for example, in the V2, everything I've coded processes whole buffers instead of single samples, which is really better because, simply of CPU cache, of CPU code and data cache. Don't waste your time doing the ultimate, most flexible, best synthesizer, bestest synthesizer of the world, because it won't work. Just try to do what you can do, and don't reach for the farthest stars. Reach for the next galaxy, not for the farthest you can find. That's one of the tricks. And then know what you're doing. It's no fun if you're a coder and you have no idea about music and you try to code a synth. And for example, you have a musician who gives input, but you don't really know what you're doing. You know that you're coding oscillators. You know that you're doing filters, but you don't know what the fuck they are for. So if you want to code a synthesizer, get synthesizers, buy them, play with them, turn all knobs, try to find out what everything does and how to get sounds out of it, and then start coding. Because if you don't know what you're doing, it can't get any good. Combinations and modulations. We need several oscillators, several filters. We need several filter configurations and everything. And people in red t-shirts are coming to drag me off. Fuck. And try to give the musician the possibility to turn every knob, to do everything in real time while the sound is running, and use modulators and.
Just go on. We just disconnect your computer.
They are stealing my computers. Very good. Give the musician the flexibility to do everything he wants, but don't make it too complex. I know that this is not easy, but this is the thing. Though the last slide would have only one word of it, called questions, with a question mark again. So, any questions? No. Oh God. Okay, so either you're totally overwhelmed or totally sucked. Okay, I don't want to know. Okay, so so I think I will come to the end now of my seminar that I prepared in 3 hours last night, and thank you.
Yeah, thanks, Kevin.
Yeah,
it was a nice one.